everyone. Welcome to Building with Strength and Investing in the Future, the Hazard Mitigating Benefits of Concrete. Today is a webinar brought to you by Build with Strength, in part with our affiliation with MIT as well. Welcome to members of the media, both from the construction industry trade press and from the men and women who are covering rebuild efforts from natural disasters all over the country, as well as to members of the construction community, including investors and developers as well. For those of you who are not aware, we are Build with Strength, a coalition of the National Ready-Mix Concrete Association, and again, today we'll be focusing on a core attribute of concrete, resiliency, especially in the face of natural disaster. Specifically, one of the things that brought this to mind here, and the reason why we're doing a webinar, has been the devastation that was brought on by Hurricane Matthew hitting the southeastern United States. But for those of you who are familiar with this, we know this is nothing new, and that cost from Mother Nature's destruction has been seen in all regions of the country. Specifically, when it comes to loss of life and property, we've seen reports from all over the Southeast, right? Starting in Georgia with $90 million in losses, North Carolina with $1.5 billion, and South Carolina with $1.5 million. More specifically, or more general actually, between 1996 and 2014, there's been $377 billion spent on rebuild efforts because of destruction. We know a lot of these places and municipalities have already started thinking how they're going to rebuild, and what we're here today to urge people to do, and what we're going to continue to urge people to do, is to rebuild in a manner that really takes into account the future, not just the here and now. And the way that you do that is by you think about resiliency. One thing that we saw in Florida after Hurricane Andrew, for instance, were laws put into place for better building codes with resiliency in mind, not just speedy recovery, but long-lasting recovery and cost savings. As I mentioned before, we've been working with MIT on this project, and they have been speaking specifically about hazard mitigation. What you're looking at right now is an infographic that was put together that outlines some of the work that they've been doing. And you can find this on our website, www.buildwithstrength.com, as well as other infographics about different attributes of concrete. We brought today with us on this webinar Dr. Jeremy Gregory from the Concrete Sustainability Hub. Now I'm going to turn it over to Jeremy to actually talk about the science behind hazard mitigation and the science behind building with strength. Dr. Gregory?
Great. Thanks so much, Kevin. Can everyone hear me? I'll take that as a yes. I hope so. Okay, good. Thanks. All right, so I'm really glad to be here. As Kevin said, we've been thinking a lot about resiliency and how you quantify that. And what's interesting, we are the Concrete Sustainability Hub and spend a lot of time thinking about concrete. But when it comes to concepts like resilience, they actually can apply to many different systems. And what I'm showing here in this particular chart is basically what we actually mean by resilience. On this chart, the x-axis is time, and the y-axis can be the performance of any kind of system. If we think about it in the context of a building, the black line shows that it has some type of performance that happens over time, and then a hazard occurs, like a hurricane or a tornado or an earthquake, that would lead to some type of drop in performance. And the resilience of the system is basically how well does it respond to that over time. You hopefully get back to that green line where you have the same performance you had before, or even a blue line where you have a better performance than you did before. But unfortunately, there are circumstances where we end up with that red line where we never quite recover. The resilience is that whole response to it. We use a really specific term, hazard resistance, to talk about that initial drop in performance, and that's really what I'm going to be talking a lot about today. Is that hazard resistance for buildings. if you go to the next slide, really our research is motivated by taking a life cycle perspective to be able to assess resilience and hazard mitigation. And I think one of the challenges is that when we think about buildings, and let's say we're talking about a residential structure here, you may end up doing a comparison between two alternative designs, one that's built to a lower design standard and one that's built to a higher design standard. They may look exactly the same from the outside and be in the same location, but one, presumably the lower design standard is going to have a lower initial cost and the higher will have a higher initial cost, but they'll have different performance over their life cycle. You know, the lower design standard will likely have a worse energy performance and a worse hazard resistance. The real challenge in the research is basically how do we quantify the benefits of that higher investment over time, and then how do we incorporate that into decisions. So on the next slide, I'm going to show what we've done in the hub, and that is to try to incorporate, in particular, hazard resistance into a life cycle cost approach. So a life cycle cost analysis, as the term implies, quantifies all the costs associated with a building throughout its life cycle. So we include those initial construction costs for building the building, its energy consumption, wear and tear, you know, doing repairs over time, but what we also include is costs associated with repairs due to hazards. And the way that we do that is combining the probability that a hazard will occur with the damage that would likely occur from that hazard. So what we include in the life cycle costs is basically costs due to repairs from hazards. And on the next slide, I'll get a little bit into how we do that. Essentially what we do is we start with the probability that a hazard will occur. And if you could just advance to that next slide. We start with a probability that that hazard will occur, and we get this from government data that basically says, you know, like here's the likelihood of a hurricane of a particular intensity, and then we combine that with what are known as fragility curves for buildings. And these basically say for a particular intensity of hazard, here's the likelihood of damage. We combine those, and then basically over an analysis period, like 30, 40, 50 years, we say here's the likelihood of damage to that structure from a particular hazard. So we can say likelihood of minor, moderate, or severe damage, and then also say here's the amount of costs associated with doing repairs to that damage. What we can do is then combine those into that life cycle cost analysis to say here's the initial costs associated with two different alternatives, and then here are the life cycle costs associated with doing repairs over that life cycle. So people are used to thinking about a payback period for things like appliances or utilities where you have higher initial costs but then lower operating costs. We don't usually think about that for buildings, and that's what we've been trying to do in this space. So let me show you an example of this in the next slide, where we looked at a residential structure in 3 different locations, San Francisco, Charleston, and New Orleans. And in each location, we looked at a minimum standard design and an enhanced design that had been enhanced to mitigate against the impacts of hazards. Now, San Francisco has earthquakes, New Orleans has hurricanes, and Charleston has a little bit of both. And what this chart is showing is the life cycle costs associated with each of these buildings. So red is the initial cost, green is costs associated with energy consumption, the purplish colors are associated with standard maintenance and then more substantive improvements, and then the blue colors are related to maintenance or repairs due to hazards, either due to earthquakes or hurricanes. And what's hard to see is that there's a darker blue color associated with earthquakes, and in this case, you can't even see it in San Francisco. So, and that's mostly due to the fact we're talking about a residential structure in San Francisco, and that there's a small likelihood of earthquakes occurring. I think this chart would be very different if we were talking about taller commercial structures. what you see when it comes to the hurricanes in Charleston and New Orleans, that the life cycle costs are much more substantive for a minimum design when compared to an enhanced design. And as a consequence, basically what that means is that for a minimum design where you haven't mitigated against hazards, particularly in New Orleans, you could be spending more money on doing repairs due to hazards throughout its life cycle than you did in that initial investment. And what that allows us to do is calculate a payback period. We're showing here in San Francisco, the curves for a minimum resistance design and enhanced resistance design basically overlap, so you don't really get much of a payback. But if we go to Charleston and also to New Orleans, you can see easily you have a quick payback of like 2 to 5 years. And these are not really significant hazard mitigation techniques we're talking about. It could just be improving the connections between the roofs and the walls, things like that, improving windows, doors. So that's why you're able to get a payback period in a reasonable amount of time. The bottom line, taking that life cycle approach really allows you to have that perspective that investing in resilience really matters. We can also move, what we've done is looked at several different locations and how this might change. Here's an example showing some different types of specific mitigation techniques that you can use in a couple different locations in South Carolina. And what we've done is actually developed this metric we call the break-even mitigation percent, and that's what's plotted here. And essentially what it does is say, let's say you don't know exactly how much that you want to spend on hazard mitigation. Well, what we can do is for a particular location, we can tell you for building design, here's how much you'll likely spend throughout its life cycle on repairs due to hazards. And so given that we know that and an initial cost, we can then say, here's how much you should be willing to invest in mitigation in order to break even throughout the life cycle of the building. Okay, so and the reason we did that is because there is some uncertainty for people about how much they'd be willing to invest, and we can show how that basically varies depending on a particular location. So this is showing basically a toenail to strap is one type of mechanism you can use to change the connection from the roof to the walls, and a gable to hip is a different type of roof structure. And so you can see that the numbers vary depending on the location. Another example that I'm showing here is basically changing the way you do a roof in a mid-rise non-engineered masonry. And this non-engineered masonry are basically terms that engineers and architects use to talk about different design approaches. So just by changing the roof, here's the amount that you would should be willing to pay depending on zip codes. And we basically run this for all the zip codes up and down the eastern seaboard and into the Gulf of Mexico. And what you can see is that darker colors mean those are locations where you should be willing to invest more in mitigation percent because of the higher probabilities of hazards that are there. And the data that we use all comes from a FEMA benefit cost analysis tool. We've just basically created our own, what we call a meta model, based on running that a whole bunch of times, which allows us to then look at many different zip codes. So you can see those numbers range even above 3%, particularly down in southern Florida, but even a couple percent in a lot of places up and down the eastern seaboard. So I have another example of basically, last one was about changing the roof. You can also go from a non-engineered wood design to an engineered concrete design, and that non-engineered versus engineered, my understanding is they're kind of just terms about basically how much thought goes into designing the building to mitigate it against hazards. And we have an example here of a multifamily building, and let's say that it's we're using a rough number of $10 million to create that building. What we calculate is that you're going to spend $500,000 on that non-engineered building in using this example of Galveston, Texas, throughout its life cycle on repairs due to hazards. Whereas a more engineered design, you would only spend $165,000, so a fraction of the cost. And so it shows you that basically you could spend $340,000 on break even expenses. So just a couple percent basically, but that can really go a long way to mitigating against the hazards. And what you can see once again is that we can go above 5% in some places that you'd be willing to invest. On the next slide, just taking a little bit deeper dive on that same type of analysis, but in the southeast where we particularly saw the impacts of Hurricane Matthew, and that you can see in some locations, you'd be willing to spend, like 9% in southern Florida there. So the basic message that we have is that, taking this life cycle perspective is really important because it allows you to understand how investments in hazard mitigation are going to pay off over time. And there are many different strategies that can be used to do that, but what we really want to encourage is those taking that perspective on how are my initial investments going to pay off in the future by mitigating against impacts of hazards. So that's all I had to say, and I have our website and contact information on this slide here if you're interested in more information. Of course, at the end, I'd be glad to answer questions as well.
Thank you very much, Dr. Gregory, for the presentation. I wanted to make one quick note. We already have some questions in via the chat function, but if anyone on the phone would like to ask a question, you can do so either by using the WebEx chat function, or if you happen to be just dialing in for the audio and not for the WebEx, you can always email me at klawler@buildwithstrength.com, and we'll get to that question as well if we have time at the end, as well as the fact that we will make this webinar available to all the participants as well as be put on the website so that people can dive a little deeper into it. And if there are any particular questions, you can always feel free to contact me as well, and we can set you up with an interview or something additional if you have any additional questions. Now we're going to turn it over to Lionel LeMay from the National Ready Mix Concrete Association. We've talked a lot about the science behind resiliency, and now Lionel's going to outline the resources available to put this science into practice. Lionel?
Thanks, Kevin. So next slide, please. What we've done at the National Ready Mix Concrete Association in support of the Build with Strength program is put together a team of architects, structural engineers, energy specialists, cost estimating specialists to help developers, design professionals design their buildings using the concrete systems. So the key to resilience in many cases is to have a solid exterior wall system combined with a solid floor system that can resist these natural disasters, especially in high wind areas where flying debris causes most of the damage, along with flooding. And of course, concrete systems have long been recognized as disaster resilient against flying debris, high winds, and also flooding damage. In addition to addressing resilience, we can also do energy analysis. So not only can you save money in the long term with regards to repairing a structure over the life of the structure, knowing that it is going to receive damage throughout its lifetime, but we can also design a structure that is extremely energy efficient, so saves money, even in the case where perhaps the damage from natural disasters isn't as high as one would have expected. You're still saving a significant amount of money by putting some investment up front for the structure. And our design team can help do that. Next slide, please. What's really important is that we're able to provide these concrete solutions at a reasonable cost with contractors and suppliers that can help build these structures. Now, concrete construction is, of course, ubiquitous. It's being used all over the country and the world, for that matter. But oftentimes, these systems that are designed specifically for disaster resilience have some unique characteristics that we need to accommodate in design. Next slide, please. So on top of that, of course, resilience has a foundation in a green building or life cycle analysis, in the sense that if you design a building that is obsolete after its first encounter with a natural disaster, that is not very green. For example, if you use super energy efficient windows, or if you use super water efficient toilet fixtures and so forth, if they end up in a landfill after the first hurricane or earthquake, that's not very sustainable. So what we can do is, as part of our design team, offer these services that can build a building not only to resist disasters, but also help lower environmental impact throughout the life cycle. Part of that is, of course, energy savings, but on top of that is using the most energy efficient, sustainable building materials available. Next slide, please. So this program is national in scope. Of course, we have headquarters outside of Washington, D.C., but we have people in the field that can help to support developers, design professionals, contractors to design and build buildings to meet these resiliency criteria along with sustainability criteria. And the way you take advantage of this program is basically you go to the Build with Strength website, buildwithstrength.com, and you go to the Concrete at Work section, and in there is an opportunity to submit a project for us to evaluate. And what we do is we produce a report that provides guidance as to how one would design a building to meet these criteria. Thank you.
Thank you, Lionel. And again, thank you to Dr. Gregory at the start of the presentation. Again, that website is www.buildwithstrength.com, and there is access to both information about hazard mitigation, and there is access to information about how to build with it in mind. At this time, we actually have some questions in via the chat function. Again, if you have any additional questions, we still have some time on this webinar. Please feel free to send them either by email or through the chat function on the webinar. The first question is for Dr. Gregory, and it says, we have seemed to focus on hurricanes. Does this metric change for other types of natural disasters or potentially man-made disasters such as fires or deterioration? So, Dr. Gregory, do you have an answer to that?
Yeah. The metric itself would be calculated in exactly the same way. What's different is the two components that really go into that estimate of how much damage you would expect over the life cycle. And the two things are, what's the probability of the hazard, and then also how much damage can you expect from hazards. So for example, man-made fires or man-made destruction, you could absolutely use it for that. It just basically then comes into how well can we estimate how frequent those fires would be, and then the type of destruction for that. So that part of the kind of the engineering assessments is actually another component of our research that we're doing, is better estimates of that, to be able to say, if there is a fire, for example, how well can we estimate exactly how much damage will occur, and then then there's a whole other assessment of basically how frequently that those will occur. So the approach definitely holds. What we need to assess for different locations is basically how well can we estimate the likelihood and the damage.
Thank you very much for that, and thank you for the question. Again, a lot of this information in this presentation will also be found on the website, both the MIT website and the Build with Strength website. And you can, if you have additional questions, you can always reach out to us or find that information there. In the meantime, there is one last question still in the queue, which is, how do you convince governments to adopt these strategies? And from a Build with Strength perspective, thank you for the question, but from a Build with Strength perspective, a lot of folks who have seen the type of materials that we've been putting out and the actions that we've been undertaking, we plan to continue to take the type of information that was shared today and share it with federal legislators and state legislators especially in these places that are prone to natural disasters, so that they can better create both laws and standards of building and stronger codes that encourage resiliency and keep that in mind as they build and as they rebuild, not just in the moment, but for the potential of future natural disasters or hazards. And there is as I said, there is an aggressive campaign on our part to identify state legislatures who may be considering legislation either that we may support, in which case we will go there and we support it full throttle, or possibly that weaken the codes, in which case we'll go and let them know the dangers that could be associated with that. And again, always sort of relying back on the science that Dr. Gregory talked about in terms of resiliency and hazard mitigation. So with that, we don't have any other questions in the queue, and we'd like to thank everybody for participating, and we ask that you again visit our website and be on the lookout for future invitations to more webinars and events throughout the country. Thank you again.